In this problem, we have that a dairy farmer notices that a large circular water trough near the barn has become rusty and now has a hole near the base. The hole is 0.3 meters below the level of the water that is in the tank. If the top of the trough is open to the atmosphere, what is the speed of the water as it leaves the hole? So I'll draw my diagram here. We have our water trough, and we have a leak that is sprung at 0.3 meters below the surface. This is going to be a Bernoulli's principal equation. So we go to Bernoulli's principal, and we write down that the pressure plus 1/2 the density times the speed squared plus the density times gravitational field times the height for the first section is equal to the second section. Now, instead of writing it as first and second section, I'm going to write this as the top of the water trough and the bottom of the water trough, because that to me makes more sense in this problem. We want to find the speed at the bottom of the water trough, which means we need to know every other value in this problem. So if I go back here, what I'm going to do is I'm going to write down what I know about the top of the water trough, and I need to know the pressure, the density, the speed, and the height. And what do I know about the bottom of the water trough? And I need to know the pressure, the density, the speed, and the height. Now my one unknown, it asks what is the speed of the water as it leaves the hole at the bottom. So we're finding that value. So I need to know everything else. Let's go with our values at the top first. And so it says, first of all, that it is open to the atmosphere. So it says the top of the trough is open to the atmosphere. That means that the pressure at the top is atmospheric pressure, 101,300 pascals. The density, since it is water, so it is water here. We know that the density is 1,000 kilograms per cubic meter. And here's where we get into an interesting conversation, the speed at the top. Now the key word here is that it is a large water trough. If you look at a large container and you have a relatively small hole at the bottom, what you're going to notice is that the speed of the water as it drops down at the top is very small. So if you see that it is a large container, or if you see that it is a small hole, then the speed at the top is approximately 0. If you were to stand and watch the top of that container, you would barely see this water level drop. You wouldn't even notice it except over a long period of time. So that's approximately 0 meters per second because it says it is a large water trough. Now the height. Now what we usually do is we call the height at the lowest point 0. So we'll call this our 0 height. And that means that the top of the trough is 0.3 meters above that. And so that is 0.3. Now if it's all a horizontal section, like let's say it's tubing that's all horizontal, then you could say the height of everywhere is 0. But in this case, we just have that the height at the top is 0.3, and so we'll call the height at the bottom as 0. Now for our values at the bottom here, besides the height, we have the pressure at the bottom. Now this hole is open to the atmosphere as well. So the pressure at that opening is 101,300 also. So whenever a section is touching the air, then the pressure is equal to atmospheric pressure. You might say, well, wait a minute. Shouldn't the pressure be larger because we are further down in the fluid? And that is true. The pressure right here is larger. So here we have a high pressure, higher than 101,300 pascals, higher than atmospheric. Here the pressure has dropped. When we put a hole in here, we have reduced the pressure. And objects always move towards lower pressure, so the water rushes towards this hole. because we've reduced the pressure, the water moves towards the lower pressure. So pressure at any spot that is open to the atmosphere or touching the air is 101,300 pascals. It is still water, so it is 1,000 kilograms per cubic meter for the density at the bottom as well. And so in these types of problems, there's a lot of assumptions that need to be made. They only gave us one value, but we know everything else. We have to look at the context clues that have been written. So now we can go to our actual equation itself. And so we have that the pressure at the top, 101,300 pascals, plus 1/2 the density times the speed at the top. Well, speed at the top is 0, so that whole thing goes to 0. Plus the density times 9.81 newtons per kilogram, times the height of the top, 0.3 meters, is equal to the pressure at the bottom, 101,300 pascals, plus 1/2 our density times our speed at the bottom squared, plus, and again, here we have the height at the bottom is 0, so those three multiplied together equals 0. So we solve for the speed at the bottom. Remember that this is, again, squared, so we eventually have to take the square root. And we get the speed at the bottom to be 2.43. We kept everything in the proper units, so we have meters per second.